Welcome. Here we have a problem from introductory field theory. So I'm going to assume that we have some familiarity with group theory and with ring theory because I'm going to be relying on some results there that I'm not going to prove. But nonetheless, I'll try to point them out and hopefully we'll have a good time. And the whole problem is about proving this interesting fact about finite subgroups of finite multiplicative subgroups of fields, which is to say for any field f, if we consider only its elements for some finite subfield of this, only the elements under multiplication. So remove the zero, just how do the elements multiply? That this group of multiplication is actually cyclic, always, which is slightly unintuitive at first, but hopefully we have 5 steps here. Hopefully by the end, we'll understand exactly why this is. So let's get going. The problem says let f be a field and f of x be a polynomial in f bracket x. This bracket x here means consider the ring of polynomials, so all the polynomials with coefficients in f. So this means that if we had f equals z5, for example, then one example for f of x is that it could be 5 equals 0 in z5, 4x to the fourth plus 3x plus 1 or something like that. So this is an example. And with that said, let's get going on part A. So part A says for all a in f, so for any element in our field here, show that there is some other polynomial q of x such that f of x equals q of x times x minus a plus f of a. And we should notice 2 things about this. So right off the bat, we have x minus a right here. This should be reminding us of roots, right? Because if a is a root of the polynomial, then x minus a will be evaluating to 0. And indeed, we see root here. So roots are going to be playing an important role in this problem, roots of polynomials. The second thing to notice is q of x times x minus a plus f of a. This looks a lot like the division algorithm, which says when we divide a polynomial by another polynomial, we get a quotient times the divisor plus a remainder. And indeed, the division algorithm is how we're going to move forward with this problem. So let's get going. So we say, given a in f, we need to find some kind of divisor, something we can divide by in order for the division algorithm to work. And what we're going to divide by is the divisor is just going to be x minus a here. So we can say use the division algorithm for f of x divided by divided by x minus a. When we do this, the division algorithm, what it guarantees for us, and I'll try to leave this equation up top there, what the division algorithm guarantees for us is that we can write f of x as some new polynomial, q of x, where q of x as desired is in this f bracket x, this ring of polynomials with coefficients in f, q of x times the divisor, which is x minus a, plus some remainder function, r of x. But think about this remainder function. X minus a here has degree 1, so what if the remainder function was something like x squared? Well, it wouldn't make sense, because if the degree of r of x is ever greater than the degree of x minus a, then we could actually pull out parts of r of x into q of x. So not only does the division algorithm guarantee this, it also guarantees a second clause, which is that the degree of r of x is guaranteed to be less than the degree of the divisor, which is here x minus a. And the degree here is 1. So because the degree of x minus a is 1 and the degree of r is less than that, we actually get that the degree of r, because it must be an integer here and it can't be negative, it must be 0. So the degree of r equals 0, which means that r of x is a constant. So r of x is a constant. Based on that, if we come down a little bit, we have f of x equals q of x times x minus a plus a constant, right? Let's try plugging in a value to see if we can figure out what that constant will be. let's see what happens if we plug in f of a. Remember, if a is a root, then this term here will act nicely for us. So f of a is going to be q of a times plugging in a for x, a minus a plus r of x. And what happens here is that because a is a root, this goes to 0. And now I don't think we need the equation anymore, and I need space, so I'll scroll down a bit. This goes to 0, which tells us that f of a is going to equal r of x. And this lines up because r of x was supposed to be a constant. So in conclusion, the division algorithm guarantees that we will be able to write f of x as some quotient function, q of x, times our divisor, which is x minus a, plus a constant, which we just learned is f of a. So this can be our conclusion for part A. The division algorithm lets us do this, and that's something that we prove in ring theory. So part B says, prove that f of x equals 0 if and only if x minus a divides f of x. What it means for something to divide a polynomial is that we can use the division algorithm and r of x, this remainder, equals 0. So something divides is just analogous to the remainder equals 0. And the question asks us to show that f of a equals 0 if and only if this x minus a term divides this. And remember how we were talking about x minus a being similar and related to roots. Well, f of a equals 0 is the definition of a being a root. And remember, a polynomial is only a root. A polynomial only has a root, if, what is going on? If f of a equals 0. So f of a equals 0 both ways is if and only if a is a root. And if we factor polynomials, a polynomial might look like x minus a1 times x minus a2 cubed times x minus a3, on and on and on, right? We can factor the polynomial into these individual roots. And in order for something to actually be a root, it needs to be in this factorization. So a being a root necessarily involves f of x in some way equaling x minus a times something else, some other quotient. But if we look at this now, when we plug in a, we will get the desired result. But in order for that to happen, we need to have this form, which is the same as the division algorithm says, except the division algorithm also tells us that r of x equals, that we have the plus r of x. So because we don't have it, it just means that r of x actually equals 0. And this is just the definition of dividing. So it's a bit of a tautology here, just a definition rage, but to divide means that the remainder is 0, and to be a root means that there can't be a remainder. So we've proven that f of a equals 0 if and only if, which can be abbreviated to if with two f's, if and only if we have x minus a dividing f of x. So this is our result for problem 2. Problem 2, of course, it's part B, but I called it 2. And finally, and this is a very important result, deduce that f of x can have at most degree of f roots. For the complex plane with the fundamental theorem of algebra, we actually show that it has exactly degree of f roots. But for any polynomial here, this says prove that it can have at most degree of f roots. How will we go about doing this? I guess I'll scroll down to get us a good amount of space. So we want at most the degree of f roots. Well, we can do this by induction. So what might our base case be? The base case here, I think a reasonable base case would be if the degree of f equals 1. Because if the degree of f equals 1, then we can write f of x as some ax plus b where a and b are both in the field, because f, after all, has coefficients in the field f. Because we can write f of x like this, we know that f of x equals 0 is really the same thing as saying ax plus b equals 0. And now, remember, degree of f being 1 means that actually a cannot be 0. So a side note here is that a is non-zero. If a were 0, then it would just be b. It would be degree 0, so it wouldn't count. So a is non-zero here. And coming back down to this equation, what that means we can do is we can subtract by b and divide by a. We get that x equals negative b over a, which tells us the important fact: there is only one root. And this proves for a base case that if the degree equals 1, there's one root, which follows that there must be at most one root for degree, at most n roots for degree n. So our base case is all set. Now let's do the inductive part, and I'll switch to new color. So now we move on to the induction. And our inductive hypothesis is going to be that a degree, if f has degree k minus 1, then f of x has at most k minus 1 roots. So if we were just starting out, for example, we would have our base case and we could say k equals 2, which is to say we're assuming that the base case is true. Well, it is, of course. And now the whole point is that given this, let's prove that if a polynomial has degree k, then it must have at most k roots. Then we can just start toppling the dominoes, toppling the integers over one by one, and we prove it for everything. So our goal now is to show that now our goal is to assume that the degree of f no longer equals k minus 1, but instead equals k. And to show that we can only have one more root on top of all these. And to do that, let's use part B. Part B says that if a is a root, then it must have that x minus a divides f of x. So first of all, I guess, there's the case where there are no roots. So this is a trivial case, but if there are no roots, then clearly we are satisfying the condition, right? We're fine. Because if there are no roots, then there are definitely less than n roots. But if there's at least one root, so at least one root, then let's single it out. We'll call it a. And what we can do is consider x minus a. Because a is a root, we know that x minus a is going to divide f of x. And remember that another way of writing this is to say that we can write f of x as x minus a times some quotient, q of x. X minus a has degree 1. And because degrees add when we multiply polynomials, this tells us that q of x must have degree of f minus 1. And degree of f is k, so degree k minus 1. Now, if f has a root, then either it must make this part of f go to 0, or this part of f go to 0. Clearly, only one element is ever going to make this term go to 0. It would be a. Q of x is less decided, but the roots of f are going to be 1 plus however many roots q of x has. Here's where the inductive hypothesis comes in. The inductive hypothesis says that any degree k minus 1 polynomial will only have at most k minus 1 roots. And by using the division algorithm, we've reduced to a k minus 1 degree polynomial. Therefore, we can say that f of x will have will have at most 1 plus k minus 1 roots, where the k minus 1 at most is coming from the inductive hypothesis, And this is, of course, the same as saying k roots, at most k roots. I guess we can write this all out. At most k roots. This is our crucial result, and it's going to come in handy on the next part of the problem that we're going to move to, which is about the groups. This is where the problem gets interesting. But just to recap, what we've done is say we can use the division algorithm, but if it's a root, then it's going to be having a constant here. Furthermore, if it's a root, it's going to divide. And because it must divide, we can use induction to nicely say that any polynomial will have at most k roots, which is to say that you can continue to break down the polynomial into degree 1 factors until you know absolutely that it cannot have more than the degree of the polynomial. It can't have more than that many roots. Now let's move on to part D. This is probably the most tricky problem because it's making that leap in the argument that's going to let us solve part E nicely. So part D says, let G be a finite abelian group. Remember that abelian just means commutative. It means that AB equals BA for all A and B in G. It's commutative here. So if this group G has at most m elements of order dividing m, for each divisor m of the order of G, show that G is cyclic. Let's break down this middle sentence because it's quite something. Let's say that the order of G was 10. Every divisor m of the order of G, so m could be either 2, 1, 5, or 10, but let's just say m equaled 5 for now. For every divisor m of G, of the order of G, there may be at most m elements of order dividing m. Okay, so perhaps here we have at most 5 elements whose order are either 1 or 5. If instead this had order 100, and m was, instead of being 5, m was 25, then this would say that there are at most 25 elements whose orders are either 1, 5, or 25, which are the factors of 25. This is saying a fact about divisors. I'm going to delete this now as we move down. It's saying show that G is cyclic if this is true. And the key is going to be that our group is abelian. So let's get lots of space here. This is part D. So G is abelian. We're going to need to make use of a fairly heavy-duty fact about abelian groups called the fundamental theorem of abelian groups. And this fundamental theorem tells us a lot about the structure of abelian groups, because it says that any abelian group, G, is going to be isomorphic, which means it may be different, but not in a meaningful way, just through some relabeling of names of elements. It's going to be isomorphic, the same shape, literally, as some direct product of ZPIs. So what I mean by this is Z is the integers, mod P is integers that are going up to some prime. So 1, 2, 3, 4. 0, 1, 2, 3, 4 would be Z5. And the direct product means, when I finish writing this now, the direct product means that the group is going to be some tuples, right? So maybe if this was 2, 3, 5, then it could be 1, 2, 1 would be an example tuple. And you can add these and multiply these component-wise. And the fundamental theorem of abelian groups says that an abelian group is structured enough to always be isomorphic to some direct product of the integers. And because we know about the integers really well, this is going to be helpful for discussing abelian groups. So we know that G is abelian. And if we just remember here, every divisor M of G has this property. So how are we going to prove this? Let's assume that we have some divisor M of the order of G, and we're going to try to show that there can be at most m elements of order dividing m. Okay, so how are we going to do this? What we can do is consider how this direct product functions. We're trying to show that it's cyclic, right? One way to show that this is cyclic is if each ZPI only shows up once. Because consider this. If G were isomorphic to Z2 cross Z2, this would not be cyclic, because whenever we had an element like 1, 1, for example, it would go 1, 1. If we added it to itself, it would go to 0, 0. And then instead of moving through all 4 elements of the group, it would just go back to 1, 1. This means that the order would not be enough. It would have an order that's not all these multiplied together, but rather the least common multiple of all of them. So in order for G to be cyclic, we need no repeated ZPIs. If there's a single repeated ZPI, then the group can't be cyclic because there will be some sense of repeating too early. If there are no repeated ZPIs, then we can take a product of all the generators, so find some generator A1 for ZP1, some generator A2 for ZP2, and go all the way on to AN. And if we take their product, so A1, A2, ... AN, this will generate our group. So this is a generator of the whole group, which would prove that it's cyclic, if and only if this is true. There are no repeated ZIs. So now our goal is to prove that there must be no repeated ZIs. And here we're going to come to the fact about the divisors. So like I said, let's assume that M is a divisor of the order of G. If the order of G were 100, M could be 50, M could be 2, M could be 10. We're just going to assume that we have some divisor. And our goal is going to be to show that we're going to almost use up our quota. Because remember that our condition says that for this divisor, G cannot have more than M elements with order dividing M. So what I want to do is show that for each divisor here, we're going to use up our full quota with exactly 1 ZPI, and therefore there cannot be more ZPIs in store. So assume we have a divisor. A divisor M of G, and because it's a divisor here, M is going to be 1 of the ZPI. So M is going to equal some PI. Or some product of PIs, but that won't matter for our case, because all we need to do is show that there are no repeats. So we're going to just use this one part of the property. So actually, probably a better way to phrase this would be consider some ZPI. So if we consider a ZPI, then PI is going to be dividing the order of G for sure, because the order of G is going to be the product of all these PIs. So PI divides the order of G, which I do write divide with this vertical line. And so now we can apply the property. So the property implies that there are at most PI elements with order dividing PI. So elements with order dividing PI. Alrighty. Now, because we have this condition, let's go through ZPI and show that actually every element of ZPI has order dividing PI. Of course, P is a prime, so we could do something with the fact that ZPI is a cyclic subgroup in of itself. But another way to see this is just to say, if G is an element of ZPI, then it's going to have some subgroup generated by it. subgroup generated by G, and this is going to have some order. And by Lagrange's theorem, the order of this subgroup must divide the order of ZPI, which is PI. So this is to say that Lagrange's theorem says that the order of any subgroup must divide the order of the group. And the order of this element here, likewise, must divide the order of the group which it is in. So the order of each element of ZPI is going to divide PI. How many elements are in ZPI? PI. So there will be PI elements in ZPI whose order divides, right, PI elements dividing PI. I guess this is with order dividing. With order dividing PI. And the condition said that there can be at most PI elements with order dividing PI. Therefore, if there were another ZPI, say if we're talking about Z5, if G was some direct product of Z2 times Z3 times Z5 times Z5, there would be two Z5s in here, and those two Z5s would make a contradiction, because the first Z5 would have 5 elements with order dividing 5, and so would the second one, and they would be different elements, and that would be a contradiction. So scrolling to the side, and then come up to the top here, what we've said is that based on this condition, the condition, actually let me switch colors so that I'm not going to confuse myself with the rest of the stuff to the left. So the condition here that we're given implies that we cannot repeat a ZPI. If we did, then we would have a contradiction because we would have too many elements of order dividing PI. And if you remember, no repeated ZPIs, that means that G is going to be the direct product of different length cyclic subgroups. And if we take the product of all their generators, if these are generators where AI here generates CPI, then the order of this here in G, so the order of the product of all the generators, it's going to equal the least common multiple of the orders of all of them, and the least common multiple of that is going to be the product of all the primes, and the product of all the primes is the order of G. Therefore, we're done. We showed that the condition means that there can be no repeats in this fundamental theorem of the Abelian groups, no repeats in these ZPIs, which implies that we can find a generator by combining all the generators of these cyclic subgroups. We can find a generator for the whole group. So that was definitely the most involved argument so far. Now, how can we tie this all together, tie together our result about roots and tie together our results about Abelian groups to show the final fact that a finite subgroup of F star is cyclic? And let's do that right here. Get rid of this line. All right, let's do that. So if F is a field, because F is a field, its multiplication is, of course, going to be commutative. So this means that, in a sense, it's Abelian. And this is going to be concrete once we're considering only its multiplication. So, in fact, we're looking for subgroups of F star, right? So consider some subfield, any subfield of F. So, well, just a second. I don't know what I'm saying. Not a subfield of F, but a subgroup of F star, just like the question's asking. So F is a subgroup of F star. We want to show that this is cyclic, because F is a field, we know right off the bat that H is abelian. And actually, the question itself only asks us to consider finite subgroups. So while we're at it, let's make this finite. That's going to be important because it's a condition that we used to prove part D. Namely, part D asks for a finite abelian group. And we can find a finite abelian group right here. It's H. So H is finite and abelian. Now, let's show that this property holds on H. So if M divides the order of H, here, if M is a divisor of the order of H, we want to show that H can have at most M elements of order dividing M. So if the order of an element is going to divide M, that means that x to the m is going to equal e, or thinking in terms of fields, 1, because we're doing multiplication here, and 1 is going to be the multiplicative identity. So x to the m has to equal 1 here. And this is true if the order of x is equal to m, or more generally, if the order of x simply divides m. Because let's say that m was 10. Let's say that m was 10. If the order of x was 2 or 5, then taking it all the way to the power of m is still certainly going to get you to the identity. So if we consider the set of all x such that x to the m equals 1, this is going to be all the elements for which it's true. So we want to show that the set of x in H such that x to the m equals 1, that the order of this set is going to be less than m, or equal, at most. And here is the kicker. We can translate back to thinking about f as a field and say the condition x to the m equals 1, this looks an awful lot like a polynomial x to the m minus 1 equals 0 in the field. And in fact, if x is in, so let's call this A, if x is in A, then necessarily, because x to the m is equal to 1 multiplicatively, necessarily x is a root of this polynomial back in F, back in the field F, is a root of x to the m minus 1. Therefore, by part D, x to the m can have at most m roots. So x to the m has less than or equal to m roots. So the amount of elements in A must be, also I wrote greater than or equal to, I meant less than or equal to, less than or equal to m roots, so the amount of elements in A must also be less than or equal to m. And so to conclude, this means that by part D, any finite multiplicative subgroup of a field, right, is indeed cyclic. F star and any subgroup as well. So I hope you enjoyed this taste of what field theory can look like. A lot of division algorithm, a lot of group theory and ring theory coming together in a really nice way. And I hope to see you next time.